Today, we're going to actually see why we've been working with Laplace transforms. And what we're going to do now is we're going to actually transform an initial value problem from T space to S space, solve it in S space, and then translate back to T space. We're going to start with a problem we know the solution to, x dot equals 3x, x of 0 equals 2. X dot equals 3x we know has an exponential solution, x equals ce to the 3t, and since x of 0 is 2, that means the solution is x equals 2e to the 3t. Now, before we actually start doing this, let's establish some notation. The Laplace transform of little x, which is in T space, is going to be cap x, which lives in S space. Okay, so since x dot is 3x, the Laplace transform of x dot is the Laplace transform of 3x. Now, last time, we discovered that the Laplace transform of the derivative of f was minus f of 0 plus s times the Laplace transform of f. We're going to apply that to x dot, and what we're going to get is minus x of 0 plus s times cap x. And then when we transform the right-hand side, linearity will give us the Laplace transform of 3x is 3 times the Laplace transform of x. So what we get then is minus x of 0 plus s cap x is 3 cap x, moving the cap x's onto the left-hand side and the other stuff onto the right. We've got s cap x minus 3 cap x equals x of 0. That's s minus 3 cap x equals x of 0, which was 2, as you recall. And when you divide through by s minus 3, you get cap x equals 2 over s minus 3. And now what we need to do is transform back to T space. The inverse transform is the inverse transform of 2 over s minus 3. Linearity, 2 times the Laplace transform of 1 over s minus 3, and 1 over s minus a transforms to e to the at. So this whole mess transforms to 2e to the 3t, which is x, which is the solution to the problem. Now, we really want to do this for second-order equations and higher, and as a result, we're going to need something about transforms of higher derivatives. Okay, so the transform of the second derivative is going to come from the transform of the first derivative, and the key idea is that the second derivative is just the derivative of the first derivative. So we take the Laplace transform of the second derivative, and that is the Laplace transform of the first derivative prime. And by our formula, that's this function evaluated at 0 with a minus sign plus s times the Laplace transform of this function, which is f prime. Okay, but we know what the Laplace transform of f prime is. It's minus f of 0 plus s Laplace transform of f. And when we write that out and multiply it out, we get minus f prime of 0 minus s times f of 0 plus s squared cap f of s. And that's what the Laplace transform of the second derivative is. It's minus f prime of 0 minus s f of 0 plus s squared times the Laplace transform of f. And now we can repeat this trick for higher order derivatives. And what you discover is that the Laplace transform of the nth derivative is this list of derivatives multiplied by higher and higher powers of s, all evaluated at 0, plus s to the n f of s. So, except for these constants here, the nth derivative is the same as multiplying our Laplace transform by s to the n. Okay, so let's take a look at another problem we've seen before, x double dot plus 16x equals 0. And we have initial conditions, x of 0 equals 2, x dot of 0 equals minus 6. This we recognize as an undamped harmonic oscillator, and undriven, so our solutions are going to be sines and cosines. But let's see what the Laplace transform method tells us. Okay, so the Laplace transform of x double dot plus 16x equals the Laplace transform of 0, and Laplace transform of 0 is just integral 0 to infinity 0 e to the minus st dt, and that's just 0. So what we've got then by linearity is the Laplace transform of x double dot plus 16 times the Laplace transform of x equals 0. So what we're going to use is what we just discovered, which is the Laplace transform of f double prime is minus f prime at 0 minus s f at 0 plus s squared Laplace transform of f. Okay, and we just write that out with x's where you see f's, and what we end up with then is minus x dot is 0 minus s x of 0 plus s squared cap x, which is this piece, and the 16 cap x is this piece. We're going to do exactly the same thing, which is move all this stuff over here, and we're going to plug in the fact that we know that x of 0 is minus 6, and x of 0 is 2. And as before, what we're going to do is we're going to divide by s squared plus 16 to isolate the cap x, and we're going to get minus 6 over s squared plus 16 plus 2s over s squared plus 16. And I've split it up into two fractions because this looks a whole lot like a cosine transform, and this looks a whole lot like a sine transform, because the transform of the cosine of bt is s over s squared plus b squared. The transform of the sine of bt is b over s squared plus b squared. The cosine is just taken care of nicely. We got a 2 times that. Now here, b is 4 because b squared is 16. So we need a 4 here. We had a minus 6. So what we're going to do is write it as minus 6 quarters times 4 over s squared plus 16. And now we're ready to back transform. We get L inverse is minus 3/2. This goes back to the sine of 4t plus 2, and this goes back to the cosine of 4t. Let's do one more problem. X double dot plus 5x dot minus 6x equals 0. X of 0 is 2. X dot of 0 is 1. So we Laplace transform the left-hand side, and that's equal to the Laplace transform of the right-hand side, and the Laplace transform of 0 is 0. So by linearity, that's the Laplace transform of x double dot plus 5 times the Laplace transform of x dot minus 6 times the Laplace transform of x. Now, using our formula for second derivatives, that's going to give us minus x dot of 0 minus s x of 0 plus s squared cap x for the Laplace transform of x dot plus 5 times the Laplace transform of x dot in our formula for the derivative gives us a minus x of 0 plus s cap x. And here we just get minus 6 cap x equals 0. And we're going to do exactly what we did previously, which is keep all of the s stuff on the left-hand side. And what we'll get is an s squared plus 5s minus 6 cap x. And we move all the other stuff to the right-hand side, sx of 0 plus 5x of 0 plus x dot of 0. And when we plug stuff in, what we discover is x of 0 is 2, and that'll give us a 2s plus 10, and x dot of 0 is 1, so we end up with 2s plus 11 on this side. we divide through by this thing, and we get something that doesn't look a whole lot like anything in the table, which is a problem because we're going to back transform. But we're going to start by factoring the bottom. Oh, by the way, that should look familiar. It's the characteristic polynomial for this differential equation. It's pretty much impossible to avoid the characteristic polynomial in any solving method. Okay, so here it's actually the denominator of the Laplace transform. Okay, so we're factoring this, and how are we going to back transform? Well, the answer is, if we could get it into a form like this, we would be able to back transform because this is the transform of e to the at. So our plan is to break this thing up using partial fractions. Okay, and we'll talk about partial fractions in detail a little later in the course, but for now, just remember that the way you do these linear things, where a product of two of them, is you put a over one of them plus b over the other, and you solve for a and b. Okay, so the first thing you do in such a situation is you multiply through by the denominator, and you get a 2s plus 11 in the top, and over here the s plus 6 cancels and you get an s minus 1. Here the s minus 1's cancel and you get an s plus 6. Now this statement is true for all s, and there are lots of ways now to proceed to find a and b. But my favorite in these situations is recognizing if this is true for every value of s, it's true for any value of s that you choose, and there are some nice values of s. For instance, s equals 1 in this term is going to vanish. So let's put in s equals 1, and we get 2 times 1 plus 11 equals a times 1 minus 1, and that's going to zero out, and we get b times 1 plus 6. So 13 equals 7b, and b is 13/7. Now another nice value to put in here is s equals minus 6, because that kills off the b term. And what we're going to get is 2 times minus 6 plus 11 equals a times minus 6 minus 1, and b times 0, which was the point of this. And this ends up being minus 12 plus 11, which is minus 1. This is minus 6 minus 1, which is minus 7. A ends up being 1/7. So we can decompose 2s plus 11 over s plus 6 times s minus 1 as 1/7, 1 over s plus 6, and 13/7 times 1 over s minus 1. Now you inverse transform. 1 over s plus 6 goes back to e to the minus 6t, because you remember the Laplace transform of e to the at is s minus a. Okay, and this goes back to 13/7 e to the t.